How's it going, everyone? This video is going to go over basic operations with vectors, so addition and subtraction of vectors, as well as multiplication by a scalar or division by a scalar. So just a quick introduction of what a vector is. In engineering and physics, vectors are typically described as a property that has a magnitude and a direction. And now vectors are not limited to that definition, but that's what we'll work with for now. So let's say you have some starting point and surface here, and you have a vector that has a certain magnitude, and the direction can be defined by the angle between the horizontal surface here and the direction of the vector. And let's say that angle is 30 degrees for this example. And we can say that this side here is length 1. And how can we calculate that? Well, let's say the magnitude of the vector is 2. Okay, so there's our vector. It has magnitude 2, and it has an angle of 30 degrees from the horizontal. Well, that vector forms a certain triangle, right? And we can calculate that the height of that triangle is 1, okay, because we can take the sine of this angle, right, and multiply it by the hypotenuse, and the sine of 30 multiplied by 2, sine of 30 degrees, that will give us 1. Okay, we can also find the base of this triangle, which is actually going to turn out to be root 3, okay, because we take the hypotenuse, multiply by the cosine of the angle. Okay, so 2 times the cosine of 30 degrees will give you, it'll give you a long decimal that'll go on, but it's actually root 3 is your answer. Okay, so you could represent this vector by stating the magnitude and direction, right? Magnitude of 2, 30 degrees from the horizontal, but you could also state it in component form. If you imagine this as being a coordinate system, Cartesian coordinate system with x and y axes, well then this point here that the vector points to, if you were to draw that vector from the origin to that point, it would have coordinates root 3 and 1. And you can represent the vector just like that, with its components being the coordinates if that vector were placed on a Cartesian plane starting from the origin and going to the point that it goes to. You just give the coordinates of that point. Those are the components of the vector, the x component being root 3, the y component being 1. And when you represent a vector in this way, well, if you need to, you can always get the magnitude and the angle from the horizontal. Okay, so let's define this vector as u. Okay, and if we want the magnitude of u, represented with 2 vertical bars on each side of it, well, that's just going to be the square root by Pythagorean theorem, the square root of one component squared, right, the base squared, plus the height squared. Okay, and that gives us the square root of 3 plus 1, the square root of 4, which is of course 2. And that's no surprise. We already knew that the hypotenuse here, which represents the magnitude of our vector, is 2. We can also get the angle from the horizontal. Okay, we know that the tangent of that angle should be equal to the height, which in our case is 1, divided by the base, which in our case is 3. So if we take the arctan, or the inverse tan, of 1 over root 3, well, that should give us our angle, which is 30 degrees. So you can represent a vector in component form, and from that you can get all the necessary information about direction and magnitude if you need to. Now there's a certain convenience to representing a vector in component form because it makes it easier to add and subtract vectors. Okay, so let's say you have a vector u, which is equal to 3 and 2, and a vector v, which is equal to 1 and negative 2. All right, so if you were to add them, u plus v, well, that would just be taking the x components and adding them, and then taking the y components and adding them. Okay, so this would give you the vector 4, because that's 3 plus 1, and 0, because that's 2 plus negative 2. Right? Now, if we want to subtract vectors, same process, right? You're just subtracting the components, right? So 3 and 2 minus 1, negative 2. Well, that would give you 3 minus 1 is 2. 2 minus negative 2 is 2 plus 2, which is 4. Okay, and that's adding and subtracting vectors. Now, this has a particular geometrical representation. Okay, so let's take our vectors 3, 2, and 1 and negative 2 and plot them. And I'm going to change colors here to make it easier to see. Okay, so vector 3, 2, 1, 2, 3, 1, 2 would be a vector that goes like this, right? And the vector v, 1, negative 2, would look like this, okay? Now, if you add the vectors, okay, what you get is a vector that actually points to a very specific place. If you were to draw a parallelogram, okay, if these vectors were end to end, okay, if you were to draw a parallelogram, okay, so this is vector u right here, and this is vector v right here, okay? Now, if you imagine the vector u being placed down here, so its starting point is not the origin, but the end of vector v. Or if you imagine vector v being placed right here, so its starting point is not the origin, but the end of vector u. Okay, you get this parallelogram. And from the origin, okay, the corner of that parallelogram where both vectors u and v start, to the opposite end of that parallelogram, that is actually what you get if you add those two vectors u and v. And if you look at those coordinates are 4 and 0, which is exactly what we calculated as adding the two vectors. Okay, what if we subtract them? Well, u minus v, that's like u plus negative v. Okay, negative v has the same magnitude as v, but it's pointing in the opposite direction. Okay, so it's actually going to look like that. Okay, and instead of 1, negative 2, its components are negative 1 and positive 2, okay? Which is, of course, what we're adding here when we're adding negative v to u, right? We're adding negative 1 to get the 2. We're adding positive 2 to get the 4, okay? So u plus negative v, which is the same as u minus v, okay? If you draw that parallelogram, that is the result that you get, okay? And the coordinates there, here I didn't calculate the coordinates, we just drew our parallelogram to the best of the drawing ability, and those coordinates should be 2 and 4, and if we look how things turn out, yeah, our artwork isn't so bad because we end up pointing right at 2 and 4. So that's the geometrical meaning of adding and subtracting vectors. Now you can also multiply a vector by a constant, or divided by a constant, or a scalar. So, for example, okay, let's use our same vector u, and that was equal to 3, 2. Okay, and I'll write it vertically here. Okay, if we multiply it by a constant, let's say some other vector v, which equals to 7 times u. Okay, well, the coordinates of that are going to be 7 times 3, and then 7 times 2. All right, so that's going to give us 21 and 14. Right, so you just multiply the components by whatever constant it is you want to multiply the vector by. Same with division, right? If we want to define a vector w as being equal to 1/2 of vector u, well, that's going to be 3 over 2 and 2 over 2, right? Or we could write that as 3 over 2 and 1. And if you're changing the magnitude of the vector in this way, right, you're not changing the direction, okay? You can multiply by a negative constant, right, by a negative scalar, like we did when we multiplied v by -1. And you could say the direction changes, or you could say the magnitude has become negative, right, so it's pointing in the opposite direction. But the vector exists on the same line, right? And if we were to multiply v by, say, 2, well, then you'd get a vector that's twice as long, but on the same line. If you multiply it by -2, you'd get a vector that's twice as long, but pointing in the opposite direction. All right, so multiplying a vector by a constant or dividing the vector by a constant will change the magnitude, but it will not change the direction. And it will change the magnitude by a factor of exactly what that constant is. If that constant or that scalar is negative, well, then the direction of the vector, you could say it changes into the opposite direction, 180-degree turn, or you can think of it as having a negative magnitude in the original direction. It's two different ways of describing the same thing, but the vector will remain along the same line if all you're doing is multiplying by a scalar. It just might point in the opposite direction along that line. Okay, and that is adding and subtracting vectors, and that is multiplying vectors or dividing vectors by a scalar. And the examples we did here are in 2 dimensions, but it works the exact same way in 3 dimensions or 4 dimensions, or however many dimensions you're working with. So hope that helps you with basic operations with vectors, and see you next time.